Hello, my name is Nikunj. I'm a second year graduate student at Department of Integrative Biology at University of Texas, Austin. Broadly, I'm interested in dispersal biogeography, that is how dispersal maintains distribution of biota. And today I'm going to discuss how dispersal maintains range limits. Historically, biogeographers have argued that species distribution is determined by biophysical constraints on species growth, such that the range limit is determined by environmental conditions for which the species' overall growth rate is zero. This environmental condition is commonly referred to as the bioclimatic limit of the species. This idea of environmentally constrained species distribution was mathematically formalized by Hutchinson using the concept of niche. Basically, Hutchinson argued that the species distribution can be inferred by mapping species' fundamental niche onto the geographical space. Using this logic, the species range limit can be identified by mapping the surface of the fundamental niche onto the geographical space. However, Hutchinson was quick to note that the fundamental niche may not always match with the realized environmental condition by the species. One possible reason why that might happen is dispersal. For example, if we consider a pair of source and sink patches that differ in habitat quality, migration of individual from source patch can maintain population in sink, which would otherwise go locally extinct. Clearly, in this case, there is a mismatch between fundamental and realized niches. Although sourcing dynamics are widely recognized as important determinant of species distribution, many distribution modelers ignore dispersal in practice. Instead, they argue that at broad spatial scales, climate determines the broad outlines of species distribution, while dispersal only operates at small length scales like 1 hectare plot. The theoretical justification for this approximation was given by Schmida and Wilson in their 1985 paper. The authors argued that the effects of dispersal should only be discernible at the length scales of species movement. And since the species mean dispersal length scales is typically orders of magnitude smaller than the length scales of distribution, one can neglect mismatch between bioclimatic and range limit due to sourcing dynamics. However, a careful justification of this claim shows that it may be incorrect. For example, an occupied sink patch near the bioclimatic limit can act as a stepping stone for individuals that migrate to colonize faraway sink patches. For example, Kanda and colleagues noted that Virginia opossums in central Massachusetts use stepping stone sinks to occupy faraway sink patches. This naturally leads us to a question: at what length scales dispersal matter? To address this question, I am going to consider a reaction diffusion model. A reaction diffusion model consists of three terms. The first term in red describes the rate at which the local population change. This change in population is due to growth of the species in blue and migration of individuals between adjacent patches in purple term. Here we use an exponential growth term which is dependent on environment as the per capita growth rate. And we use a two-dimensional diffusion operator to approximate dispersal. So in this model, the species fundamental niche is given by environmental conditions where the per capita growth rate R is greater than 0. And the realized niche is given by environmental condition where the species intrinsic growth rate is greater than 0. Note that the realized fundamental niche and the realized niche and the fundamental niche may not be always equal. So just by looking at this equation, we can draw two conclusions. Let's say the gray line represents the zero growth rate. Consider a sink patch where the environment is bad for species growth. So species should go to extinction in this source patch or in this sink patch. However, migration from surrounding patches can compensate for decreasing population to yield a net increase in local growth rate of the population. This corresponds to the case where migration from sources can maintain sink populations. We can also imagine an alternative scenario in which population is locally growing, but migration of individuals drive the local source population to extinction. In this second scenario, we see dispersal can actually drive the source population to local extinction. This is somewhat surprising result as the original formulation of sourcing dynamics by Ronald Pulliam did not consider these demographic consequences of sinks on source patches. Now, to formally to formally examine how dispersal affects demography and sourcing patches, I consider a two-dimensional landscape with a gradient in environment along x-axis. The black line in the middle is the bioclimatic limit of the species. I start my analysis with species present at location with environmental conditions corresponding to the fundamental niche. This starting condition means that initially the range limit of the species is aligned with the bioclimatic limit. Since the growth rate at the bioclimatic limit is zero, any change in the population at the range limit is solely due to dispersal flux across the bioclimatic limit. And since the bioclimatic limit has equal number of occupied and unoccupied patches, the influx and the outflux rate cancel each other to yield a net zero dispersal flux at the range limit. Therefore, in the case when the bioclimatic limit is a straight line, the range limit is coincident with the bioclimatic limit. However, dispersal flux will be non-zero if the bioclimatic contours are curved. For example, in the upper half of the plot, the number of unoccupied patches is greater than occupied patches. This will yield a negative dispersal flux at the species boundary. As a result, the range limit will move backwards. The gray arrow here shows the direction and the magnitude by which the range limit deviates from the bioclimatic limit. Similarly, in the lower half of the plot, the dispersal flux at the bioclimatic limit is positive due to excess of occupied patches. As a result, the range limit will move forward. Here is an animation that I created that shows the species boundary where the species boundary will stabilize for this particular geometry of bioclimatic limit. The range limit will eventually stabilize when the sum of immigration and birth is equal to emigration and death. We can mathematically show that delta E, which is difference in the environment at the range limit and the bioclimatic limit, is proportional to the curvature of the bioclimatic limit, which is a measure of how round the bioclimatic limit and determines the relative influx and outflux of individuals at the species boundary. We also empirically tested this theoretical prediction in the context of savannas and forest. According to the theory that we developed for savannas and forest, we found that the difference between the precipitation at the savanna forest boundary and the bioclimatic limit should be proportional to the curvature. So if we plot the precipitation at the savanna forest boundary as a function of absolute curvature, we should get a V-shaped curve. We found that the savanna forest distribution in Africa is consistent with the theoretical prediction. So it seems that there is some evidence that sourcing dynamics may operate on continental scales. In fact, using the model, we can now answer a very fundamental question, that is, what life history characteristics will lead to significant deviation of species range limit and bioclimatic limit. To do that, we define a new variable E tilde, which is the ratio of environment at the range limit and bioclimatic limit. We can mathematically show that E tilde is equal to 1 plus minus this additional term that depends upon A tilde. We call this A tilde as non-dimensional area, which is a function of species life history traits and climate. So by looking at this equation, we can see that when A tilde is small, E tilde deviates from 1. As a result, the range limit deviates from the bioclimatic limit. So now we can in turn ask for which life histories A tilde is small. Now looking at the expression of A tilde, one can argue that A tilde is small for a highly dispersive species with low growth sensitivity to environmental change. Intuitively, what this basically suggests is that if environment is not too bad in sink patches near the bioclimatic limit, migrants from the source patches can maintain population in faraway sinks by hopping over intermediate sink patches. And in this way, the effects of dispersal may be substantial at length scales that are far greater than the mean dispersal length scales of the species. These findings have wide implications for biogeography theory. For example, bioclimatic models are often used to draw inferences about the ecological and evolutionary processes that maintain distribution of biota. These bioclimatic model works in two steps. First, the fundamental niche of the species is estimated using occurrence data, and then this niche envelope is reprojected back onto the geographical space, either in the same region at a different time or an entirely different region. Our analysis suggests that for species with fast dispersal and low growth sensitivity, inferences based on these bioclimatic models may be misleading because of two errors. First, bioclimatic models may end up sampling environment from sinks and fail to sample environment from sources. Basically, what this means is that the estimated niche volume may not match with the fundamental niche. Second, even if we could construct the actual niche space using biophysical experiment, when reprojecting the niche space onto geography, the bioclimatic model may fail to predict occupied sinks and empty sources. From this analysis, we can draw two big conclusions. First, the range limit of the species is not only determined by environment, but also dependent on sourcing dynamics, which are mediated by the geometrical shape of the bioclimatic limit. Second, for species with fast dispersal and low growth sensitivity, sourcing dynamics may be substantial even at large spatial scales. Uh, Finally, I want to acknowledge the contribution of my collaborators, lab mates, and colleagues. And I also want to acknowledge funding from University of Texas, Austin. If you want to know details about this work, you're welcome to go to this bioRxiv version of the manuscript. Alternatively, you can also email me and visit my website to see the manuscript. Thank you for your time.